I have to set a couple of things straight. Number one, I am not on Cybron's payroll. I get no money from Cybron. I am on their advisory panel. We do meet annually and we discuss different things, but I have no financial interest in Cybron. Yes, I do own some stock in Cybron, but I do not get any royalty for anything that's purchased. I have absolutely no vested interest financially in Cybron. Having said that, there are two other things that I have to admit before I start. Number one, like Fred, I am a pulp lover. I'm not going to ask for a show of hands because I know what would happen if I did, but of course it's a Chicago guy, so I'd count the vote, and I'm sure there'd be a lot more pulp lovers in here. The second thing that I will admit publicly, and this is almost like coming out of the closet, but please don't misunderstand me, I'm not coming out of the closet. Even after 2 or 3 or 4 readings of the emails from Ken Sirota, I still don't know what the hell he's trying to say. Let's talk about instrumenting the root canal space. Let's talk about cleansing and shaping. And I think we all understand that one of the key goals in canal preparation is to widen the canal while maintaining that pre-existing morphology. And I think there was a lot of discussion this morning, both from Cliff and from John, about what the final shape should be. But the final shape ought to also be dictated by what the canal gives us and what the canal morphology is. We know we have to clean it. We know we have to shape it. A big change in the way I look at root canals over the last 30 years is we agree that they all have to be cleaned, and you have to get rid of all the remnants of organic material, and you have to get rid of the bacteria. We also have to shape them. And I think files do the shaping, and basically they're shaping it so that we can fill the entire root canal space. The cleaning is done by the irrigants. And I think there's unanimous agreement on most of our parts that, you know, if you create the right shape, you'll get the right amount of irrigation, you'll get it where you need to get it, and you'll end up with the results that you're looking for. How do we do it? I'm going to talk about the K3 file system. I'm going to try not to bash any other file system. One of the things that I agree with Cliff the most about, and there aren't many things that I agree with Cliff about, but the one thing that I do agree with Cliff about is that all the files are good. And they all have some positive aspects to them. They all have some negative aspects to them. We each have to decide amongst ourselves, what is it that we want, how do we go about doing it, and what file is going to give us the best opportunity to do that. I've used the K3, it was introduced in the United States in January of this year. I probably had it about 3 months before. I picked up a couple of them when I was at the IFIA meeting in Spain, and I treasured them until I could get more. But I've had what I would consider to be limited experience with them only because of the limited availability. Now, in order to understand the K3, and I think John did a tremendous job this morning of explaining to you about rake angles and flute design and all the rest of it, but I think it was almost to the point of coming from an engineer, and I am not an engineer, so I'm going to try to give it to you as a clinician, as an endodontist, and as I see it. We've been stuck in the past, limited into what we could do with files. We basically had limitation into the materials that we could use. There were only 3 design specifications that we could really monkey around with. We could monkey around with the taper, we could monkey around with flute configuration, and we could do something with the tip configuration, and we could get involved in technique. There was a show of hands this morning, and I think Cliff asked, how many of you started at the apex and worked your way up? And I'm sure that if we did it by age, you would see that those of us that have been around for a long time always started at the bottom. That's the way we were taught. So these were the design considerations that could come into play in this situation. Those same people who would put their hand up for starting at the bottom probably remember carbon steel instruments, because that was the first instrument that we really had. Carbon steel instruments were fine. It was the easiest way to identify an endodontist because carbon steel instruments almost all had metal handles, And I mean, if you took a week off to go fishing and you came back to your office, you had sore fingers when you had to pick up those metal handled instruments again. And then stainless steel came along, and over the years, I think the stainless steel instruments themselves have actually gotten better. And then nickel titanium. My introduction to nickel titanium was a rotary file that John McSpadden taped to a letter sent to me. It was in a metal, a U-shaped tube, and the letter went on to say, this is a new material for files, take it out and see what happens. And I pulled the file out and it went perfectly straight. I put it back in and it followed the curve, and I pulled it back out and it went perfectly straight. And I didn't see the significance of it at all at that particular point. I have learned to love nickel titanium. Why nickel titanium? It's 500% more flexible. Because it's more flexible, it's going to do a better job at negotiating canals. There's going to be decreased instrument breakage. There's going to be a decrease in ledging and transportation. And it's going to be faster without sacrificing quality. Now, go back to decreased instrument breakage. There's a learning curve. You know, it's when I talk to audiences of general practitioners, I always say, the longer you practice, the less you find the mesial roots of lower molars to be calcified in the apical 1/3. They're calcified a lot when you first start. The learning curve for learning to use nickel titanium rotary instruments is great, and you will have some problems with them, and you'll have problems with all of them. It just takes time for you to develop it. So eventually you'll get to that decreased instrument breakage, and with decreased instrument breakage obviously comes the element of safety. Cliff pointed that out. That should be number one on the list, and that is safety. It shouldn't be speed. It shouldn't be final shape. It should be safe, because obviously we could design, if we think about an endodontic root canal as a hole to be drilled instead of a hole to be shaped, if you just think about it as putting an instrument over the top of it and drilling down, we could make a better instrument to do that. However, would it be safe? And the answer is no. So I think safety has to be important, and that's one of the reasons why nickel titanium has that safety thing, because of the flexibility. Now, the old design files, you know, you had K files and Hedstrom files and Reamers and Burns Unifiles, and now there's a whole series of new designs that have come out, and has been pointed out in the past, the advances or changes in endodontics over the last 10 years, the four things that Cliff identified, it's been absolutely fantastic. I mean, I go back to a period of time when you could put an endodontist into apoplexy by raising the cost of a package of 6 files from $225 to $245. And we thought, my God, they're going to put us right out of business. And we always were a fantastically lucrative specialty simply because our overhead was so low. But now there are new designs, and there's investments in microscopes and motors, and it's gotten a lot like stereo equipment. Harvey, it's got to last for more than 3 months because it's too damn expensive. But the stuff changes very, very rapidly. And if you want to stay on the leading edge, you have to be aware of the fact that there's going to be even new designs that are going to come down the road. Let's go back and look at some of those file considerations as I understand them. And I'm going to try to simplify it and not be too engineer-oriented. We can deal with taper, we can deal with flute design, we can deal with tip geometry. These are once we got past the metal and into the nickel titanium, the next thing was, what can we do to change the design of the file? We all talked about taper, we all know what taper is, but sometimes it's good to go back and to re-understand that Mike Hewer, who preceded me as president of the American Association of Endodontists by a number of years, spent 15 years of his life trying to get ISO standardization for an O2 tapered instrument. And once he did, he was reluctant to give it up, and I think that's why the O2 taper instrument lasted as long as it did. Before Mike got involved in doing that, each manufacturer's taper was different. And you couldn't pick up a 15 file from Kerr and use it with a 20 file from Premier or vice versa. You couldn't switch back and forth because the tapers were different. And they agreed that each millimeter that you move from the tip of the instrument to the handle should increase by 0.02 millimeters. That was agreed upon until someone came along, who shall remain nameless, and decided that maybe we ought to think, when you think about the eventual shape of the root canal and what you'd really like to do when you're finished, it made sense to change the taper. And to go from an O2 taper to an 06 taper means that over that 16 millimeter working length, you are going to triple the size of the instrument in the coronal aspect of it. Boy, all of a sudden, you're not going to take that instrument all the way to the apex and work from the apex backwards. you're going to have to redesign and rethink about the way you're going to use it. What about the flute design? Boy, there was a lot of discussion about flute design, and to be quite honest with you, I don't understand a tremendous amount of it, but I'm going to try to explain to you what I do understand. The contact file, which was the first rotary file that I used, had an interesting flute design. It does have a positive blade angle. Now, where do I get that information? I have to get that information from the engineers, because I am not an engineer. I am not about to take heatless stones or some other grinding wheel and grind down a file and try to decide whether it has a positive or a negative rake angle. If the engineers tell me it has a positive rake angle and the cross-sectional pictures that I see say it has a positive rake angle, then I have to buy the fact that it has a positive rake angle. I was not in on the design of it. I was not in on the engineering of it. I think if it has a positive rake angle, then it's going to shave dentin. Radial lands. Do we need radial lands? Don't we need radial lands? I'm going to try to tell you what I understand about why each of the files has or doesn't have the different components, and then from there you can decide for yourself whether you want that feature in your file or you don't. John DeRosier, who's at Cybron as an engineer, puts it very well when he says, everything is a balance. You know, if it has a positive angle and you increase the positive angle, you can increase it to the point where the file will basically engage in the wall and it won't move. I mean, so it's all a trade-off. The radial land width, the helical angles, all the rest of the things, you play a balance, and based on that balance, that gives you the performance of the instrument. The wide radial lands give it some strength. It tends to center it. The surface that's reduced behind the radial land, now this is something that makes a good deal of sense to me. Because if you relieve that area behind the radial land, you do have a place for the debris that you're trying to remove to go. And it's going to go, by file design, it's going to go coronally, and it's going to come out. So I do think that reducing the area behind the radial land, while still giving it the width, does reduce friction, and it does help in removing the dentinal mud. That's the biggest problem that we have to deal with as far as what happens with our files. And as the flute angle, flute angle becomes larger as you go up towards the handle, it's the same design idea. The debris has a place to go. You're basically channeling it and pulling it out. If you look at all of the other files that are out there and you look at their design, you can understand where the debris is going to pile up behind the cutting edge. And if you pile up enough debris, and Cliff pointed it out this morning when you said, you know, you sometimes have to take the file out and you have to clean the file, and suddenly it goes down, because once the file is loaded, it's not going to do what you want it to do. I go back to a time when the late Henry Kahn and I at Loyola were thinking about hand files and all of the dentinal debris that you built up on a hand file and how to clean it. And you know, you've all passed it through a 2x2 and you've done it through a piece of rubber dam and you put it in a cotton roll. We bought very small little ultrasonic jewelry cleaners, and we would take the file out of the canal and dip the file into this ultrasonic solution, take it back out, and it would just immediately blow the debris off. You have a perfectly clean file, and you go back into the tooth. The problem was we were using sodium hyperchloride in stainless steel bowls, so our ultrasonic units lasted one day. And then we went to glass ones, but we were thinking in terms of how to keep the flutes from building up all of the debris. So the contact file was the first one that had those reduced radial lands, and as a result of that, behind the cutting blade, there was places for the debris to go. And you could watch the debris come out coronally, and you had a different feeling to it when you used it, because it just didn't feel like it was bogging down. And so many times when they bog down, they're bogging down because the flutes become jammed with material. If you look at this picture, an SEM picture of the K3 file system, you'll see that it's an entirely different design, but it uses many of the things that the contact file brought to the marketplace first, and it incorporated them into the K3 with a good deal of thought. The SafeEnded Tip. Contact comes with an active cutting tip called a safe cutting tip, and it also comes with a non-cutting tip. To my way of thinking, the non-cutting or safe-ended tip, the safe-ended tip is the only one to use. And I say that universally. Again, there's a temptation to think that if I have an active cutting tip, and I think in terms of canal preparation as drilling a hole, then I ought to be able to take that file, put it over the hole, step on my pedal, and force it down. And boy, that's just not the thing that you want to do. So I like the safe-ended tip. I like the fact that the safe-ended tip is going to give me less transportation. Is there a place for an active cutting tip? I think so. And I think that it probably comes in the hands of someone with a considerable amount of experience. Again, we're talking about the overwhelming number of endodontic procedures that are done in the United States, if not around the world, are done by general practitioners. And you have to kind of approach this from that standpoint. John, I know you don't like cookbook, and I'm going to do a little bit of cookbook, but my feeling is that if you don't have a starting point and you don't have some guidelines to work with, that what ends up happening is I'm going to come along and I'm going to have heard something about light speed, and I'm going to heard something about Quantec, and I'm going to pick up a Quantec file and I'm going to run it at 2,000 RPMs, and I'm going to send you a bunch of broken files. Or I'm going to take a light speed and I'm going to run it at 350 because I heard 350 is the ideal speed to run it at, and then I'm going to break all sorts of light speeds. So I think that we have to have some guidelines, and if I have to put in my own opinion, the safe-ended tip is the way to go. I don't know what the definition of a third-generation file is, or even a fifth-generation composite or bonded material, but I think the K3, knowing where we have gone or come with files, is the third generation in the design. It's triple fluted, it's asymmetrical. Look at that last one. It's safe. It's safe. And we can agree or disagree on a lot of things, but it's going to be very difficult to disagree on whether that instrument is safe or not. There are a number of things, number of characteristics that the K3 file has. And we're going to discuss each one of them individually. We're going to talk about the access handle. We are going to talk about the rake angle. We're going to talk about the helical flute angle. We're going to talk about the width of the radial lands. We're going to talk about radial land relief. We're going to talk about the appearance of a third radial land, because remember, a Quantec file only had 2 lands. This is the addition of a third radial land. We're going to talk about the core diameter. We're going to talk about the tip configuration, and then we're going to talk about the color coding and how you can tell one from the other. Is there anybody in this room who's doing endodontic procedures on the maxillary second molar that wouldn't like to have about 5 extra millimeters of space? If you are, and you don't need that 5 millimeters of space for the upper second molars, I'd like to know what your patient population base is, because where I come from, 5 millimeters is an awful lot of space when you're trying to work in that confined area. The access handle, because the handle itself is shorter and it fits into a handpiece that has a smaller head, you end up gaining 5 millimeters of space, a considerable amount. All of us have had the experience with a patient where you say, can you open just a little bit wider? And they open just the smallest amount, but it allows you to have straight up and down access, and it just changes the nature of what it is that you have to do. So the K3 Quantec come with an access handle. Does it have a positive rake angle? Does it have a negative rake angle? Again, I have to look at what the engineers tell me, and the engineers tell me it has a positive rake angle. What does that mean? Most of the files have a negative or neutral rake angle, and from a purely rake angle standpoint, if it's negative, it's going to scrape. If it's skewed towards the neutral, it's going to scrape. And if it has a positive rake angle, it's going to cut. And if it's going to cut, then it's going to shape dentin in a different manner than it does if you scrape it. What about variable helix? What do we mean by variable helix? What we mean is that all these files are ground. They're ground by 2 wheels at the same time. They're not twisted the way they used to be. But think of the variable helix as the space between those cutting edges, and think of it as a file that's been twisted. And what's basically happening is, with a variable helix, is you have tighter, smaller turns at the apical end of the file, and you have wider spaces as you go coronally. It's very important, I think, for debris removal. The angle, the helical flute angle, changes as well, so that at the apical end you have a smaller flute angle than you do as you go coronally. Again, what is the shape that I want to achieve? How do I best achieve it? How do I want my instrument to work so that the debris is in fact moved out? Part of the learning curve situation is to take extracted teeth and to work with extracted teeth. And when you work with extracted teeth with any rotary system, you will find that you push less and less debris out the apical foramen in your hand than you ever did with any hand instrument. Now, if you're pushing it out, if you're pushing it out with a hand instrument, or you're pushing less out with a rotary instrument in your hand, you're doing the same thing in a clinical situation. So does it, in fact, maybe relieve some of the problems we have with postoperative discomfort? I'll tell you what, it's amazing how little debris comes out in your hand when you are using a rotary instrument. If you're using a rotary instrument that has a variable helical flute angle, less and less debris is going to come out the apex because it's going to be forced out the top. And it tends to also reduce the screwing in effect as well as assisting with debris removal. Now, there was some discussion this morning about whether these things really do screw in or screw out, or they don't. The worst specimen or example we get to use is the plastic block. It's not analogous to a clinical situation. It's horrible. I think the reason we use it is because it allows the person who's examining the file or trying the file to see exactly what it is that the file is doing. But tell me in what clinical situation you ever get to see what the file is doing. What happens is you bog down the file, the plastic melts depending upon how aggressive you are, comes up all of the flutes, and bango, you break the file. Take a plastic block, take anybody's instrument, and see whether you can push on it and make it screw in. Quantec screws in, Pro Taper screws in, Profile screws in, the K3 screws in, but the K3 screws in, in my hands, it just feels like I'm not losing control. In many of the other ones, if it grabs, particularly in a plastic block, forget it. I can't get my foot off the rheostat, nor can I get the torque control to act fast enough not to suck that thing right down the block. So by changing and having a variable flute angle, it does eliminate some of the screwing down. This is probably the closest that I'll get to being an engineer, and I'm not an engineer, but think of this. You have to think of the pitch as the number of turns or threads over a given distance. And what happens in many of the files is that they have a constant pitch. So over each 5 millimeter, 7 millimeter, 10 millimeter increment, you have the same number of turns or twists. And as a result of it, you have constant pitch, which is what you have with a profile. If you take constant pitch, you have symmetrical geometry, what you end up with is a screw. And it looks like a wood screw. And it acts like a wood screw. And you all know what happens when you take a wood screw. You know, wood screw, unlike a stainless steel screw, a screw that's used for metal or for stainless steel, a blunt-ended one, it doesn't engage. You have to force it in. If you take a wood screw based on its shape and you get into the hole and you start putting a little bit of pressure on it, it gets sucked down into the wood. And that's basically what happens with an instrument that has constant pitch and symmetrical geometry. If you take a K3 instrument and you look at it and you measure the number of turns or threads over a given distance, you'll see that it's different. It has more twists or turns in the apical portion of it than it does in the coronal aspect of it. It's not a screw. It has a variable pitch, and therefore it doesn't feel like you're going to lose control and it's going to suck you down inside that canal. The width of the radial land. I think this is significant, and this is probably one of the most significant aspects to me of the K3 file, and that is the fact that if you look at the width of the radial land on a U-shaped file, you'll see that they are all the same. And the radial land is what gives you an increase or a decrease in the strength of the instrument. Obviously, if strength comes from making the radial land wider, then you could make this radial land go all the way to here, and then make that one go all the way to there, make that one go all the way to there, and so on. And when you're done, the instrument basically wouldn't turn. Remember, there's a balance, and you're always balancing all these different properties to try to come up with the file that does what you want it to do. What the K3 has done is, here's your land. It's relieved on the back side of the land, but look at the width that you gain. But it's not engaging any wall back here. But you still have the width, which gives you the strength. You have a wide radial land here, you have a wide radial land with relief there, and then you have this funny one down here, and that funny one down there doesn't have any relief behind it, and the engineers tell us that that's what keeps the instrument centered within the canal. It also controls the amount of cutting that you're going to get, because these two cut just as efficiently as that one does, but they have a better channel for debris removal. So it's a significant difference in the width of the radial land. If you have no relief behind it, this is the entire edge that's engaged on the wall. This is the area that's engaged on the wall, and now you have space behind it for the debris to be removed. The addition of the third radial land stabilizes it, it centers the instrument, and you notice it's not relieved. There was some discussion, there was some rolling of eyes at the AAE meeting in Chicago at a cross-sectional view of a K3 instrument that someone else showed that, I mean, it didn't look like this at all. Now, how that was created or why it was created or even if it was created to make a point, this is what the cross-sectional diameter, the cross-section of a K3 file looks like. It's uniquely different. The variable core diameter. This is significant, and it's a significant difference in what Cliff is saying about the fragile nature of the apical 1/3 of your GT. In this particular case, you don't want to, and rightfully so, you don't want to engage that couple 3 or 4 millimeters at the tip of your file. You don't want debris to be building up in there. You don't even want it to engage the wall. What the K3 has done is it's increased the core diameter. In other words, the core diameter, the relationship between the core diameter and the outside cutting edge, you have a thicker core diameter at the apical end of the file than you have as you go up. So the apical end of the file is stronger than the coronal aspect of the file because you have more core material. So if I'm going to use that file and I want it to engage something in the apical 1/3, I'd like to have additional strength down there. And you can read it yourself, and basically all it says is the diameter to the outside as opposed to the core. The core is bigger at the apical end of the instrument, significant in eliminating problems of separation or breakage. We talked about the SafeEnded tip. To me, it's the only tip to use. Now, let's talk about the color coding system. Color coding system is, at an ACE meeting 2 years ago, we spent the better part of half a day trying to decide how to color coordinate these things so we could understand. They divided us up into small groups. They said whatever group wins can stay in Orlando for another 2 days. Tell us how to design these. And what they did was they took the best ideas of all of the groups, put it into one. Nobody got to stay in Orlando, and they came up with their color coding system. It's a 2-ring system, and the top ring is going to give you the taper, and the bottom ring is going to give you the file size. So what you're going to see here is the 04 taper is green, the 06 taper is orange, and the tip size is a 40 because it's black. And we're, again, going back to the same thing that we all knew from the very beginning in endodontics. You know, it was black and green and blue and red and orange and yellow and so on down the line. So it's a unique system in that you can tell when you're looking at the file in the sponge what size the taper is, what size the instrument tip is. The problem is by the time most of us see it in the microscope, it's in the handpiece. So it's your assistant who has to know the color coding part of it. That's the hardest part about giving a hands-on course, because the participants are always running up and saying, is this the right file? And you look at the color. At least with the K3s, you can figure it out. With the Quantec, I rely totally on my assistant to know what color comes after which, because there just isn't any rhyme or reason to it. But this is a pretty good compromise in giving you both the taper and the tip size on the handle. We talked about the screwing in effect and why, what are the characteristics of a screw that would closely resemble what happens with a lot of the other rotary instruments. They're symmetrical. The only ones that are not are the race file and the K3. They have constant pitch. They have radial lands and flutes that stay consistent. They don't open up. The space doesn't get any bigger. And the helical angle stays the same all the way through. The U file, symmetrically placed lands, equal land width, symmetrical in cross-section. K3, asymmetrical, unequal lands, asymmetrical in cross-section. Significant difference. You decide what it is that you want. You decide which one feels the best in your hands. You decide how you want to use them. They have significant differences. And again, I'm not going to put one down over the other. Obviously, I saw the hands, and there are more profile pro taper users and GT users in this room than there are K3 users in this room. Try them. Try them. Give them a shot. Third generation, triple fluted, asymmetrical, safe, cuts very effectively, and cuts quickly. It's the K3 file system. Now, how's it used? Two different types of instruments. orifice openers to open the coronal portion of the canal, and a K3 to complete the apical preparation. Presently, the orifice openers are nothing more than Quantec flare instruments. Now, if it was a perfect world, I would have them come up with a system where the orifice openers had the same design as the K3, simply because you have to use the orifice openers in a slightly different motion than you have to use the K3s. The series that I would like to use, and again, it's cookbook, but it works to explain to a large group of people what it is that you're trying to accomplish, how best to accomplish it, and then you conclude your remarks by saying every technique turns out to be a hybrid. If you have the time to stay on routes for any length of time, you will notice that everybody has their own idea of what file follows what file, and everybody kind of steals from one. And I mean, it's truly a hybrid. It's a bastardization. There is no cookbook technique. Everybody tries something different. But as a starting point, you need to have a uniform system that you can then use to evaluate this file compared to that file and say, you know what, I think I like the orifice openers better than I like the gates, but I like the S1 before I like something else. So again, keep an open mind, but cookbook is the way to start and to develop it for the first time. And I think you use the 06 as your first instrument. It's a great flaring instrument. Lots of people who use profiles like the 06 as a starting instrument. Then you use a 10 taper and an 8 taper. They all have a size 25 tip. And I'm trying to do exactly the same thing that Cliff talked about, and that is I'm trying to get straight line access. I'm trying to open the coronal aspect of it. I'm trying to do all of that so that I can really do what I want to do, which is to prepare the lower 1/3 or the apical 1/3 of the canal. The significant difference between using a K3 file and using a Quantec file is that when you use that Quantec file as an orifice opener, you don't just push it in and take it out and push it in and take it out. You have to peck with it. If you don't peck with it, it will either engage too much and you'll have it begin to unwind. In teaching general dentists how to do it, invariably the instrument that they have the most problem with is the flare, and they don't break it as much as they just unwind it. So the idea is to basically peck with it and peck away and advance in 1 millimeter increments. I can't do quarter millimeter increments, not anymore. I don't think I could have done them 30 years ago. Not only couldn't I see them, even if I could see them, I couldn't get my hand to work that way. It just didn't work that way. The K3 comes packaged this way. It gives you the taper, it gives you the length. They come in 21, 25, and 30 millimeter lengths, and they have tip sizes that vary from 15 to 60. They come with 04 and 06 tapers, and I'm not sure if the 02 taper is in development or if it's ready yet. I don't really know, but I can tell you this. My preference in all cases where I can is to use the shortest length possible. I just like the feeling of control that I have with a 21 millimeter as opposed to a 25 or a 30. Again, you get what the canal gives you, you get what the tooth gives you, and if I can use a 21, then I would prefer to use a 21 as my instrument of choice. Electric motors, constant RPM. I will admit, I guess I should have admitted this up front with those other disclaimers that I had. I did try the profile in the beginning. I used the air-driven handpiece with the turtle and the rabbit. And, you know, there's 11 operatories in my office and 4 partners, and if I happen to be in the last operatory working with that air-driven handpiece, and 4 of my partners all jumped on the handpiece, all jumped on the airline at the same time, I never had any constant torque. And I did have some profile failures, and I threw the system out. I just said, no, I don't want any part of this. So when I started back with rotaries, it was tough for me to overcome that problem. The problem, I think, was that if I had started with an electric handpiece with constant torque and constant speed, I wouldn't have had the problems I had with the air-driven handpiece. So we can talk all we want about the instruments, and John knows probably 1,000 times more than I do that they don't all work the best at 350. Some work better at 320, some work better at 380. Eventually, I think we'll come up, here we go with the ideal world. We'll take a file, it'll have a barcode on it. The barcode will tell you what the best speed, what the best torque control is. It'll automatically set it when you put it into the handpiece, and it will work most efficiently. But until we reach that point, we need to set some guideline. So 350 is fine. It's amazing when you're teaching technique course and you're teaching people how to do this, how slow 350 RPMs are. I mean, they sit there and they look at this thing and they say, it has to go faster. It has to go faster, because they're used to a high-speed handpiece turning at 400,000 RPMs, not at something at 350. Constant torque. Do we need torque control motors or don't we need torque control motors? Another long discussion at an ACE meeting. Lots of the endodontists in the room said, by God, that's an insult. We don't need torque control motors. I mean, we ought to be able to tell, and we shouldn't need the assistance of a mechanical device to keep us from over-torquing an instrument. And my comment to that was, I wonder if all of the surgeons around the world are sitting down right now deciding that they don't need robots in the operating room. You're still driving the robot. You know, what I like about the surgical robot is that it puts in a suture exactly the same way, with exactly the same tension, and exactly repeatable time after time after time after time. There's nothing wrong with torque control, and torque control on a motor, I think, makes you better able to understand how far you can push a rotary instrument. And when you start off, with a great deal of torque control and you're into the ones or the twos on a scale of 1 to 6, you'll find that what you learn is how to develop that light touch, because, you know, when this thing keeps beeping at you, you begin to realize that I might be doing something wrong. So there's absolutely nothing wrong with it, and if you're really macho and you don't care, then take the torque control off. You can shut it down, have no torque control, and you can be in complete control of the whole situation. Sometimes at my age I take little mini mental vacations, and I like the torque control. I like the torque control because it's going to tell me when I've taken one of those mini mental vacations and I push down too hard. Light pressure, don't force the instrument apically. I think that that's been pointed out all morning long. The file should be rotating. You know, there's another misconception, and the misconception is that you place the file in over the canal where you want it and then you start the file. Wrong, because if it engages anything, it's going to take off on you. So the idea is to have it moving whenever you enter or exit the canal, have it moving. Copious amounts of irrigation, and advance it in an in and out motion. Now, the K3, remember the Quantec or the flaring instrument, you basically had to peck with that one. Now all of a sudden you're getting a K3 instrument where you really want to put it in and take it out. Put it in and take it out. Unlike real world endodontics that says 4 instruments, 2 swipes, that doesn't work for me. That doesn't work for me. I can't do that. Nor could I say that that's exactly how you ought to use the instrument. Anybody's electric motor works well. I happen to like this one. This one has an automatic reverse feature on it. And what I like about the automatic reverse feature, it means that as long as you keep your foot on the rheostat, if you encounter the torque control, so the torque control says you've put too much torque on, it will automatically back the file out, and as long as you don't take your foot off, it keeps going backwards. Now, what's the significance of that? It doesn't come forward until you lift your foot off the pedal and set your foot back on the pedal again. In the others, where it automatically backs out and beeps, anything from 1.5 to 2 seconds later, it starts forward. Now, if you haven't found out what the problem is, if you haven't removed it, if you haven't looked at the file to see if it's unwound, it can start forward again. If you're in one of those mini mental vacation modes, 1.5 seconds isn't long enough, and it can start forward again before you've ever disengaged it. So I like the fact that with this motor, I am in control. If I have my foot on the rheostat, and it's well, you talk about the learning curve. You all know what happens. I mean, when an alarm goes off, if you got your foot down on the accelerator and your speed control button goes off or your radar detector button goes off, you take your foot off. Okay? When that motor beeps, you have a tendency to want to take your foot off. And if you take your foot off and then you realize what's happening and you put your foot back on, it's locked in and it drives it forward. So you just keep your foot on the pedal. That's basically all you have to do. Irrigation. I am in the #1 minority in owning this Quantec irrigation unit. I don't know that they sell a couple dozen of these a year. It's fantastic. And if you ever had one, you'd never want to go back to non-irrigation. It's a unit that fits on top of the electric motor. There's no cross-contamination in the system at all. Basically what it is it uses a peristaltic type pump that just rotates. These wheels rotate. Here's your solutions. You have your choice between 2 bottles. You can use whatever 2 systems you'd like. And the hose just runs through, down to the handpiece, the wheels keep turning, and they pump the material out, so there's no reservoir, there's no cross-contamination, and it's continuous, it's automatic, you can use 2 irrigants if you like, and it's a standalone unit. The disadvantage to it is that it clips to the handpiece with a hose, and it's a little bit more cumbersome to work with. But if you want to see debris move out of a canal, as you start using this instrument, and it starts rotating and the pump goes on, you will watch little shreds, little white ribbons of dentin come right out the top of the tooth and wash away. I think one of the reasons why the system hasn't been terribly popular is a lot of people thought that they needed to use sodium hypochlorite with it, because that's what we always irrigated with. And that's fine, but it's a bit of overkill under most circumstances. You can always go back and use sodium hypochlorite, and I advocate that, but I use it simply with sterile distilled water, which acts as a lubricant and gets rid of all the debris. The other nice thing about it is, and Cliff, you mentioned, you know, when you have a problem and you pull a file out, you always want to look at the file. Make sure nothing has happened to the file. While you're poking that file into the sponge and looking at it, my file comes out already clean, because it's like a washed field preparation. Basically, that file is rotating in a bath of whatever you'd like it to rotate in. If you'd like to rotate it and have continuous replacement with sodium hypochlorite, you can do that. If you want to do it with EDTA, you can do that. If you want to switch back and forth, you can also do that. So it's a neat adjunct to use with your electric motor. Now, what's the technique? Cookbook. John, close your eyes. Straight line access. I disagree with you, John. I think straight line access is critical, and I think straight line access can be achieved without sacrificing an overabundant amount of tooth structure, but it's critical to the use of the file. Locate the canals, ultrasonics. I think ultrasonics we've gotten away from ultrasonics in many instances, and I think the next step after you've located the canals is to go in there with an ultrasonic with a CT4 tip and just blow out all that stuff. Get rid of all that junk that you're trying to work around, and get a visualization of where you are by removing all of the debris. Establish a glide path. The Cybron technique card that they give out says that you establish the glide path with a 6 up through a 15 or a 20, and you only need to go down about 2/3 of the way. Wrong. And I agree with Cliff on all the reasons why you want to establish a glide path and what you can tell from that glide path. You can tell more about the canal anatomy. You need to know what the canal anatomy is. You need to know whether you have a type 2 canal system that's going to come back together again. You need to know if you have a bayonet, if you have 2 or 3 curves. And the only way you're going to do that is by hand instrumentation. And you can't throw away those small hand instruments. So start with whatever you want. Again, do whatever the tooth will give you. You may be able to start with a 15. You may even be able to go all the way up to a 20 without a problem. In the same light, you may end up with a 6, or you may end up bending a great number of 6s trying to get all the way down. Once you've established a glide path, then use whatever system you want to establish your working length. Whether you're going to use an apex locator, a digital radiograph, or even a conventional radiograph, whatever you're comfortable with that's going to tell you what the working length is. Take that 06 Quantec flare instrument, size 25 at the tip, follow it with a 10 flare, follow it with an 8 flare, but remember this, stay in the straight part of the canal. Those flare instruments are not meant to go around curves. If you just look at it diagrammatically, you have your estimated working length, 6, 8, 10, 15, confirm the working length. If you're into patency filing, then at any time along the way, feel free to take an instrument and establish patency. I cleaned that one up a little bit. 17, the 06, the 10, and the 8. Take it down to resistance. I heard this morning you don't like the term resistance. I think resistance is there. You can change the semantics of it any way you like. I kind of like what you said about, till it doesn't make any more forward progress. The idea is stop before you think you have to force it down. And if you do that, you're going to have a lot less problems. So don't force it down. Take it to what the canal will give you. Now, addressing John's concern, and I think it's absolutely correct, of not following an instrument of the same taper or the same tip size, just arbitrarily start with a 4504. Maybe you'll start with a 4004. Maybe you'll start all the way up with a 50 or a 5504. Go 0445, go 0640, go 0435, go 0630. Check patency at any time that you want. If, in fact, you're using the pump, you have all the irrigation going on that you possibly could need, and even more so. The apical preparation, you can take an 0425. If the 0425 goes to the apex and you gauge that to be enough, then you're finished. If you would like to have a larger preparation, if you'd like to take the 06 at 25 to working length, go right ahead and do it. But you can only do what the canal will give you. Don't try to make it, because you'll get yourself in trouble if you do. Go ahead and confirm the working length, gauge your apical foramen. Okay? Again, just follow the steps down. I know it's cookbook, but the only way to evaluate this file and evaluate someone else's file is to have some consistency, and then with the consistency, you can make whatever changes and adjustments you like. You have a couple other options. Okay, everything else is exactly the same. Straight line access, locate the canals, ultrasonic, establish working length, 06, 10, 8, straight part of the canal. You could use all 06. If you don't believe that John is correct, and you shouldn't follow the same taper with the same taper, use all 06 instruments. Take 0640, 35, 30, maybe you'll start with a 50, maybe you'll start with a 40, maybe you'll start with a 35. But you stay with the same 06 taper. 0625, and then maybe even an 0620, if that's what you want to do. To your desired length, confirm it, gauge the apex, and you're ready to go. Now, what do these things look like? If you look at that top picture, boy, I mean, how many root canals have we seen that had that bottle shape? Okay, that's the old gates. The idea was absolutely correct. If you don't clear this, there's no way you're going to get down to here. Okay, I kind of like this tapered. You know, it just looks like I like it better. You know, is it better? Is it better than this? If it works and you're able to accomplish what it is that you'd like to accomplish, then it's fine. GT rotaries. I mean, Cliff, you addressed the issue right in here where maybe you'd like to have that a little bit fuller in that area. Maybe you'd like to have a little more preparation. I think the K3 will give you that. So will yours, but you may have to go back in order to do that. I think the K3 is going to give it to you, not on one file, one swipe, and that's real cookbook. You know, you have to do it until you have accomplished what you want. Will it accomplish it? You know, even Fred, I'm sorry, but even pulp lovers sometimes, you know, it happens. It happens. Okay. Good news. These instruments are less likely to fracture. I would say that it would be extremely difficult to separate an 06 instrument. Not quite as difficult to separate an 04, but it's very difficult to separate an 06 instrument. Okay? Jerry, you talked about using the PAC-MAC, putting it in at 21 and taking it out at 20. These go in at 21 and come out at 16. Okay? And when they do, there's not much you can say other than that. Okay? That is a true clinical x-ray. I would imagine at this point everybody's hungry and ready to go to lunch. My final word is this. They're all good. They all have some real positive properties. You have to experiment with all of them. You have to try them all. Then you settle on whatever one it is that you like. There's no sense if you like one to bash the other one, because in someone else's hands, that other instrument may just be the instrument of choice. Thank you.